Let A, B, C, and D be real numbers. The two curves, y is equal to ax squared plus c, and y is equal to bx squared plus d, have exactly 2 points of intersection precisely when one of these options. Okay. Well, let's understand this geometrically. In fact, I'm going to work through this entire problem more or less geometrically. First, understand that we have two parabolas, and both of the parabolas are symmetric around the x-axis. So both parabolas will look like this, or, well, I'm not drawing this very well. They're symmetric around the x-axis. Okay, so the other thing to keep in mind, if the vertices of the two of them are like this, if one of them opens downwards and one of them opens upwards, then that definitely works. And when does this happen? This case is when this happens when the two intercepts are like, we don't just need one intercept to be greater than the other, because we could have had the parabolas going like this. Okay, so we would need let's write out what the two things are. I have y is equal to a squared plus c, ax squared plus c, and y is equal to bx squared plus d. Okay, so this case happens when c is greater than b and a is less than 0. C is greater than d. A is less than 0 and b greater than 0. Or c is less than d and a greater than 0, b less than 0. The other thing we're going to have to be careful about here is that a and b could be equal to 0. So in fact, we could have less thans and greater thans here, but they can't both be equal to 0. Because then, we have two horizontal lines, but a single horizontal line, totally fine. Okay. The other way that the other sort of visual way that these things can intersect is one parabola looks like this and the other looks like this. So when does this happen? Again, so C is greater than D, and A is less than B, but both have to be positive. Or we can have D greater than C, and 0 is less than B is less than A. But then we can also have some similar things with them opening downwards. Yeah, a lot of these. So again, I don't like using process of elimination completely here, but all four coefficients will matter. So options A, C, and D in the multiple choice cannot possibly be correct. I also suspect that option B is not correct. Option B says A over B is less than C over D. But like in some way we could just, it's essentially without loss of generality, we could let one of C or D be equal to 0. And it's really only the difference between the two that matters. So, I mean, I'm inclined to sort of just skip through working out all the logic and just say that the answer is option E. Okay, so again, the reason I'm saying this is because the values of C and D just work as a vertical shift for everything in the geometry. And so without loss of generality, we can just shift everything so that one of these parabolas always passes through the origin. You know, that might happen when C is equal to 0. So if I just set C equal to 0, then I need the relations between A, B, and D. But none of the other relations, you know, could potentially even make sense. So I mean, and there we also see even, you know, the C minus D, the fact that these are vertical shifts, it really only depends on whether one parabola is above the other at the origin, and then we're comparing the sign of these two things. You know what? Maybe there's a purely algebraic way of figuring this out. If I set these things equal, yeah, we didn't need to do this geometrically. Let me think of this as in a different way. And hopefully we can just derive this directly through algebra. If the two curves have exactly 2 points of intersection, this says that ax squared plus c is equal to bx squared plus d has 2 solutions. So I have a minus b x squared is equal to d minus c. So x squared is equal to d minus c over okay, hold on. Let's just look at this equation here now. Okay, if d minus c is equal to 0, that means either a minus b is equal to 0 or x is equal to 0. And in either case, that means there's either one solution, x equals 0, or there's infinite solutions. Okay, so we know that d minus c cannot be equal to 0. So let's suppose it's positive, d minus c greater than 0. Well, that means, I mean, x is real. We're talking about curves in the plane here. If this is positive, then we need, if there are going to be 2 solutions here, if this is 0, then there are no solutions. If it's negative, there's no solutions. So a minus b must also be positive. And we can work out the logic in the other way as well. If d minus c is negative, then we must have a minus b is negative. And so that, combining all that together, it says that d minus c and a minus b either have to be both positive or both negative. And that's exactly what this says. Yeah, so we didn't have to work this out geometrically, but it's also nice to see. It's also nice to see what you are working with. I'm not sure why I went for the geometric approach right away rather than the algebraic approach. Maybe it's because of the question I worked on immediately before this. No, it wasn't, because the one I did right before this was very algebraic. But that was the first thing that came to mind, was to sketch this out and work the answer out that way. So yeah, I didn't have to use process of elimination here. I could have derived the answer directly. But yeah, sometimes it's good to just go with your first instinct and only stop when you realize you've definitely hit a dead end of some sort. Thanks for watching.